In this project, we analyzed the figure skating jump sport, a highlight of the upcoming Winter Olympics, using computer vision. Our system marks key points on athletes using MediaPipe, and our LSTM achieves 99% accuracy in jump classification. By integrating rotation counting, we transform raw video into professional-grade Olympic analytics in real time.
If you enjoy our content and want to see more, don't forget to hit subscribe.
Hello everyone, in this project we will be making an ice skating figure jump analysis project all using computer vision and deep learning. As we all know, there are different types of figure jumps like Axel, loop, toe loop, Lutz, flip and many more. Total there are 6 types of figure jumps. We will be making and classifying them on the basis of how the skater moves and how the jump is done. We will also be implementing that how many revolutions does the person does while he is in air. As you can already see in the key features, like there are automated jump classification. Like I said, we will be using the LSTM model for classifying that Axel, Salchow, toe loop and etc. And kinematic rotation counting for counting that how many revolutions does the person did while he's on air and doing the skating. And also we will be using the MediaPipe to track the 33 key points in the body, and these have various real world application, like in Olympics also we can use it, like the Winter Olympics which is coming, it can be used there as well. It is also used in professional coaching to the skaters who are preparing for the world events and many more. So first we need to prepare the dataset for it. I downloaded 720 clips for this project from a GitHub repository. You can simply also download from there. I have classified the dataset into 4 classes, like the first is Axel, the second one is Edge, third is complex pick, and the fourth is simple pick. The class 0 and class 1 consist of edge skating, in which there is no toe assist from the another foot, whereas in the class 2 and class 3 there is a toe assist. These consist of Lutz, flip and toe loop. First I show you some clips of this skating. As you can see in the left side, this is my complete data set. For this I have 720 clips, like this is for the Axel. Similarly I have for the edge also, like these are for the edges. It consists of both loop and Salchow. The third one is of simple, like here consists of toe loop, and the last one is of complex pick. It consists of flip and Lutz. First I show you the Axel. So you can see this is the clip of the Axel. Here you can see the skater is doing the Axel jump. Now I show you some of the edge. This is of the loop. Here you will see the skater is doing of loop, and this one is of Salchow. So these 3 are the edge skating, in which the person doesn't take the help of its another foot to get the jump. Now we'll see the foot assisted jumps. The first comes to the flip. This is flip. You can see the person hit his foot in the ice so that he can get some jump. I'll show you again. You can see the person hit it on the ice so that he can get the jump. This is the flip. Now the Lutz. It is also a foot assisted jump. See, here he also uses foot to get the jump. And the final toe loop. This is the toe loop. So these are all the 6 kinds of jumps. We will be classifying into 4 types. As I mentioned earlier, the complex pick consists of Lutz and flip, and the edge consists of Salchow and loop. We will also be demonstrating that how many revolutions does the person did when he's doing this jump. First of all, I downloaded my dataset from the GitHub and set the output part of here, organized dataset, and then classified into 4 classes. As I mentioned earlier, it will be classifying on the basis of, because the data was a bit jumbled, so I classify based on the title present on the clips, so that I get the 4 datasets, like the Axel, edge, complex pick and simple pick I got here. So the files are successfully saved in and organized in 4 classes. Now the first step involves that we will be extracting some random 50 frames from the same 20 clips that we have. We will be extracting them so that we can perform the annotations on the labeler platform, so that we can get a bounding box across the scatter, so that when we use the MediaPipe function on it, then the model doesn't confuses it with some extra background noises or any other person coming in the frame. It will only detect the scatter having in the bounding box, so that it can mark the key points on it. So I show you how I use this code to get the 50 frames from it. I simply use this code to get the random any 50 frames from the same 20 clips that I have. And in the next step, you can also annotate your custom dataset using Labeler. I uploaded the 50 images that I got to the Labeler platform, where I performed the bounding box annotation and just imported the data in the COCO JSON format. And later you can convert that COCO JSON format to the YOLO format. Here is the 50 images that I got. All these images come from the 720 clips that I have. Now I'll show you how I did the annotations on the labeler platform. So here you can see the annotation. I have just marked the bounding box across the scatter. Simply I had done for all the 50 images that I got. You can see here I have also marked the bounding box here. Similarly here as well, the scatter has been marked correctly. It is just to remove any background noise from it, so it cannot detect any other person as well, like some people are standing here. So the MediaPipe model will only track only this person and look at this bounding box only. Now coming back to the code. After you complete your annotations on the labeler platform, you can simply download your result in the COCO JSON format and upload that COCO JSON format in the project folder here. And then you just need to clone this library of labeler. After git cloning this library, you can use this function called COCO to YOLO converter. This will help to convert your COCO JSON format into the YOLO format. After running the code, I got my annotations in the YOLO format. Now comes the part of the model training. We will be using the YOLO 11 Nano model and epochs will be of 100. I simply run this code to train my model, and after the results are being stored here. Here I got my batch.pt file. Then I simply run the inference on a raw footage. I use the bytrack function so that the model can always track the scatter in all the frames. I show you the output that I got from it. Here you can see the output that I got in the inference. The scatter has been marked properly by the bounding box. Now we will be using our MediaPipe model to run the inference on our video to get the 33 key points on the video. We will also be using our best.pt file which we just got, so that the MediaPipe can focus on the bounding box only. And we'll also provide 0.2 padding, because the bounding box often doesn't catches the whole scatter. It might detect some limbs of the scatter as well. So to prevent that, we have provided the 0.2 padding on it. So this is the code for it. I have run it for all the 4 classes to show you the inference. Now I show you the inference of it. So this is for the Axel. You can see MediaPipe has formed all the 33 key points on the scatter. This is for the edge jump class. You can see the all the points having marked. And this one for the simple pick jump. And this one for the complex pick jump. So this is all the code for the getting the inference on the MediaPipe model on it. Now we come to the skeletal feature extraction pipeline. In this step, what we will be doing is that we will run all the 720 clips by using the MediaPipe model, and we will also provide a 0.2 padding as we provided earlier. And after we get all the 33 key points, we will store them in a NumPy format so that the LSTM model can be easily trained on the NumPy format. So this is the code for it. I have get all the 720 clips in the NumPy format. I show you. Here I got all the processed skeleton frames. See the extension .npy, it's for the NumPy. Now comes the main part of LSTM training. In this step, we will be making a LSTM neural network architecture. The sequential input will be of 150, because each video is of 5 seconds and it is a 30 FPS video. So 30 into 5 gives 150 frames, and each frame has 33 key points and 4 coordinates in it. Is x coordinate, y coordinate, z coordinate, and its visibility. So total makes 132. So the size is of 150, 132, and the first layer will be of LSTM. It will be using the bidirectional layer, and we'll also provide a dropout layer so to prevent any overfitting in it. And the final output dense layer will be of softmax so that it can classify the jump into 4 categories that we made. So this is the code. We have imported all the sequential LSTM, dense layer, dropout layer, bidirectional, and the optimizer add-on function as well. Now in this step, we'll be providing the normalization to the all the skaters, because in certain camera angles the skater is far away and in certain camera angles the skater is very near to the camera. So to prevent any scaling issue, we will provide the normalization, like we will be centering his midpoint of the hip 2 points to be at its midpoint and scaling the torso height so the camera angle distance will not matter anymore. And also we'll be flattening the 33 key points and its 4 coordinates to a single row. Like here we have converted the 33, 4 to 132. So this is the code for it for normalization. Now comes the part where we will be making the architecture of a neural network. As I said before, we are using the bidirectional LSTM. There will be 2 layers of bidirectional LSTM. One will be the dense layer where the activation function is redo, and the final dense layer will be of softmax. So you can see the neural network architecture that I created. We have used the activation function to be tan edge. Earlier I used the ReLU, then the efficiency in the training doesn't come good, but while using the activation tan edge, we get the efficiency of 99%, which is really good. As I said before, the dense layer is of ReLU and the final dense layer is of softmax. Now comes the part of model training. We had splitted our data into 80% to be training and 20% validation. As you can see, 576 NumPy files for training and 144 for validation. And we are running for 100 epochs, and our output will be saved as a .keras format. So here we run our model. After 100 epochs, you can also see the efficiency accuracy is coming to be 99%. And is lost very less. I have also plotted the graph for it so you can visualize it better. You can see the model accuracy is increasing and the validation accuracy is also increasing. So it confirms that the model is not overfitted, because if the model was overfitted, the validation accuracy will be kept low. And similarly for the model loss as well, both the activation and validation graph is very low. Now comes the real-time jump and rotation analysis. We will be using the .keras file that we just got after training our model. You can also see here I got the model, and we'll also applying the rotation logic. What we will be doing is that using the midpoint of the both hip points, we will be calculating the total angle that the person rotated. By this, we can get the total number of revolution the person did while he's on air. See, I have marked all the actions, like if the jump is categorized to Axel, so it will display that it's Axel. Similarly for edge jump, complex pick and simple pick. And here comes the logic that I told you about. We'll be using the left hip and right hip coordinates, and by adding and dividing by 2, so we get the middle point, and we'll now calculate the current angle of it, and by total revolution the person did, the angle changes and we get the total revolution that the person did. So this was the whole code for it. Now I show the output that I got. Here comes the Axel jump. You can see it's scanning. The total revolutions have come to be 4 and categorize it as an Axel jump, which is correct. Now comes the edge jump. You can see the total revolutions have come to be 2 and it's classified as edge, which is correct. Now comes the complex pick jump. You can see the MediaPipe has properly marked the body and it has all classified it as a complex pick, which is correct, and total 3 revolutions. Now comes the simple pick jump. You can see it's scanning and the total revolutions are 2 and it has classified as simple pick, which is correct. So this was all for the project. I hope you like the video, and you can also check our other YouTube videos that Labeler posted, and also stay connected to our social media platforms. Thank you.
If you'd like to explore practical resources and hands-on examples, we've created a dedicated GitHub repository. It's filled with cookbooks covering computer vision, AI agents, and more. Link is in description.